Hey everyone, it's Chronic Blaze here, and welcome back to another video. Well, it happened. I'm currently busy with exams, if you saw by the short that I posted, so you know what that means. I don't got time to make videos. Yeah, I really wanted to use the holiday break to upload, but then there was this massive physics assignment that I had to do on quantum computing, and I was like, well, looks like I'm not getting anything done here. But what if I just combine those two ideas? See, physics completed video that I'm submitting in less than 24 hours that honestly is pretty good, and YouTube channel. Well, do I have a story for you? Hopefully everything's scientifically valid here? Yay? The computer, a device that seemed niche and nerdy 40 years ago, has since redefined everything we do. Since becoming mainstream in the 1990s, everything from entertainment, financial management, communications, statistics, medicine, education, calculations, automation, and complex analysis have been dominated by the computer. The standard computers of today have changed the world, but what if I told you that computing is headed in an entirely different direction? A direction unknown to the machines of today, but instead powered by something totally new, with limits that can only stretch the imagination. Quantum physics is a relatively new branch of physics that was originally used to demonstrate how electrons behaved. What was found is that the standard Newtonian laws of physics don't apply at the subatomic level. Quantum mechanics, which are mathematical representations of the wave-like nature of particles, do instead. And this is being used to fuel new revelations in the field of computing, where the only limit is your imagination. So come along for the ride as I explain to you the power of quantum computing. Currently, large supercomputers are being used to solve modern-day computational problems. And while these massive computers that often take up entire rooms are fast, when it comes to complex problems with many different variables, they're actually painfully slow. Conventional computers represent their information in bits, which can effectively be in one of two states, a 0 or a 1. These states can be represented in multiple ways, but the bit can only be in one of these states at any given time. A computer can then read this binary data, which is made up of a string of 1s and 0s, and convert this data to something that the user can understand. The power of these computers is given by the central processing unit, or CPU, which contains millions of microscopic transistors. These transistors are essentially small switches that can block or allow an electric current to pass through or amplify that same current. Changing the state of these transistors helps the computer process the binary 0s and 1s, and to make the computer more powerful, you'll need to add more transistors. The problem is that eventually you'll run out of space. As problems are more and more complex, more transistors are needed to solve them. And since computers are only truly good at processing one instruction at a time, these computers simply aren't fast enough to solve modern day problems. And that's where we get to quantum computing. Currently, quantum computers have no such limitations and are able to create large, multi-dimensional computing environments that can be used to quickly solve complex tasks. Quantum computers are currently around 158 million times faster than the fastest supercomputer we have. If a supercomputer took about 25 seconds to generate 5 million random numbers between 1 and 1,000, a quantum computer would take 1.58 times 10 to the negative 8 seconds to do the same thing. This massive increase in speed is all caused by the quantum processing unit, and what exactly does that contain? Qubits! Essentially, qubits are like the quantum equivalent of bits, but they're made out of any material that can experience quantum mechanics, such as electrons or photons. Now, there are multiple ways to make a qubit. One of the preferred methods is by using superconductors. They're made of materials that, when cooled, can allow an electric current to pass through, and the direction that this current takes is the state of the qubit. IBM and Google both use superconducting qubits, but then you have Intel who wanted to be different and said, what about spin qubits? Spin is the property of a quantum particle to rotate, with each quantum particle having its own spin number. It essentially allows the quantum particles to behave like magnets, meaning it can only have one of two orientations, which are assigned to the qubit values. These have the benefit of a higher operating temperature, and theoretically just a square millimeter could contain billions of them, as opposed to superconducting qubits, which need more space. But the problem is that's very far from where we are today. All in all, while there's many ways to make qubits, superconducting qubits continue to be the leading method. Just a few qubits can outperform even the greatest supercomputers known today. As you add more and more transistors to a CPU, the power of that CPU will increase linearly, but with more and more qubits, the power of the computer will increase exponentially. And that's all because of three fundamental principles of quantum physics: superposition, entanglement, and interference. Superposition is based on the idea that quantum particles are believed to be affected by wave theory. Jeffrey Taylor discovered this by testing how many photons he would observe from a light with increasingly more filters. He found that with dimmer light, 2 photons were rarely in the box at the same time, leading him to discover that all quantum particles were affected by wave theory. Basically, quantum particles such as photons can exist anywhere within an electromagnetic wave, which you can think of like a ripple in the water. Depending on how much interference you get within that wave, which again I'll reference later, increases the likelihood of finding the quantum particle there. But the takeaway here is, we we don't know exactly where that particle is located, just that it's somewhere in the wave. And thus gets back to my favorite part of quantum physics. We don't know if something is there or if it isn't there until we look at it. So statistically, there is a chance that Koegawa is on Mars right now. This same logic can be applied to qubits. A standard bit, as we've discussed, can only be a 0 or a 1, but because of superposition, a qubit can exist as a 0, as a 1, or as both. The qubit will always have a set probability in being in one of those states, and then once the qubit is measured, it will take that state. Because a qubit can represent both states at the same time, this makes quantum computing much quicker, and it allows an advanced computational space to be created. And remember how I said the power of a quantum computer increases exponentially? Well, that's because as you add more and more qubits, thanks to superposition, the quantum computer will get exponentially faster, which offers huge performance gains over the non-superimposed linear bits of today. Then we have entanglement, which is when two quantum particles, such as qubits, are so closely correlated that regardless of distance, they can't be thought of as independent from one another. Whatever you do to one of them, you do to the other, and whenever you measure one of them, you measure the other, and nothing else can interfere with it. Einstein loved it so much that he called it spooky action at a distance, and that's because you're having information move faster than the speed of light, which before its discovery was thought to be impossible. Once one entangled qubit is superimposed, all of the other ones are superimposed as well, and once you reveal the information about one of the qubits, the information is revealed for all of the entangled ones. This is needed for any kind of quantum algorithm, and it's used often for large number factorization and searching. And finally, quantum interference, which happens during the meeting of two waves. When the waves come in contact with each other, you'll either get constructive interference, where they build on each other, or destructive interference, where they cancel each other out. It's really similar to the idea of a photon moving in a wave-like formation. I hinted at probability earlier, but the probability of a photon being in a specific position is greatest in the locations where the wave undergoes constructive interference. Having a higher wave amplitude, which is caused by constructive interference, can be used with superposition to attain the exponential speedups. We can also use this principle to bias the qubit so that when its state is measured, it'll have a greater chance at taking on the state that we want it to take. Because of these probabilities, now you're able to have so many more potential combinations of data. Say you have two standard bits. Well, that's 4 potential combinations of values, but because of interference and superposition, the qubits can be 1, 0, and both at the same time, which helps to result in the exponential growth I mentioned earlier. So by harnessing fundamental principles of quantum mechanics and qubits, a quantum computer is much more powerful than your standard computer. But there's two other advantages they have: size and energy consumption. Now, obviously, this is much larger than this, but when you compare it to... yeah, why wouldn't you want this? Add to the fact that quantum computers use less energy than the massive supercomputers, and why wouldn't you want them? And on top of that, quantum computing can be used for so many useful applications. Atomic modeling. As you go to model elements with more and more electrons, it's basically impossible to model all of the potential states of that element with a conventional computer. But with a quantum computer, because you have so many changing variables, no problem. Simulations of labs are actually possible now, which reduce the cost of materials needed to do the lab. That's already helpful to simulate the chemistry inside lithium-ion batteries, which is helping some companies figure out how to improve them. Different shipping routes and traffic simulations to find the most optimal route of travel can easily be done on quantum computers. These are near impossible to simulate with a normal computer because you have so many variables constantly changing at once. Actually, any sort of analytical predictions with more variables would be easier. Anything from chemical reactions, weather predictions, financial applications, artificial intelligence, probability-based computations, and machine learning theoretically, but I'll leave that last one C3, I guess. Then there's my personal favorite of quantum cryptography. Because nothing can interfere with entanglement and you don't know the state of the qubits due to superposition, how are you supposed to hack something if you don't know where it is?
You don't.
But of course, there's disadvantages. Making a single qubit could cost around $10,000, so this awesome revolution isn't exactly cheap. Add to that, because quantum computers are so much faster, they could crack any of our current data encryption methods relatively easily. So basically what that means is all of the secure data from the FBI, government, banks, Google Drive is not secure with quantum. Society as a whole is going to need to worry about securing all of that. Add to that, quantum error correction is really difficult. To fix a classical computer error, it's basically what IBM calls a bit flip, where something that's supposed to be a 0 is instead a 1. But with quantum computing,
Now you don't know what it is.
because you have so many possible states, it's way more difficult to fix an error. And coming from someone with at least some coding experience, this would not be easy. And of course, the cooling. Superconductors need to be cold. How cold for a qubit to be created? Well, just over absolute 0. Helium isotopes are used to cool qubits right now, but they can't remove heat that fast. And any change in temperature can potentially remove that qubit from superposition. On top of that, the fridges need to be pretty massive, which removes any ability of a quantum computer looking like this. There are other ways to cool quantum computers, such as using lasers to get atoms to emit photons, and there's ways with spin qubits to avoid the temperature requirements needed for quantum computing, but at least right now, temperature still appears to be a big issue. Since the first quantum computer was made by Isaac Chang, Neil Gurhenfeld, and Mark Kuiberneck, there's been an arms race between a bunch of companies to harness the innovation's power. IBM's a leader in this, with several commercial use machines and a current maximum of 244 qubits in their projected quantum system too. Startup IonQ's working on laser cooling, saying that's more compact than what IBM and Intel are doing, and Microsoft has a service called Azure Quantum, which allows anyone he went to develop programs and run them on quantum computers through the cloud. Hey, I needed a bridge here because I was location-based stuff. Anyways, master's or PhD program, you need that for these jobs. Such as being a quantum software engineer. They're responsible for controlling QPUs, generally through automation by code, so basic knowledge of quantum languages is needed. Qubit researchers find out the best types of qubit CUs, and because of the amount of approaches different companies have, they're desperately needed. They need to know all about the different types of qubits as well as how the company has made their system. There's also quantum algorithm researchers who find ways for quantum computers to solve complex problems, as well as figuring out how current algorithms can be used in the real world. There's plenty of other occupations such as quantum cryogenic engineers who work on the cooling systems or quantum machine learning scientists, but I think I'll stop there for the video. We're in an age where technology is constantly advancing, and at least for a nerd like me, it's so cool to see where computing's going. Even if a quantum computer may not have any benefits for the average user, knowing that this exists is still super awesome. I'll always cherish the past and how we were able to get to where we are today, but it's very interesting to see where computers are going tomorrow, powered by nothing other than quantum physics. God, why am I agreeing to post this?